Is it going? Okay, I'll begin with in the audio. As you can see, the audio bouncing. Okay, excellent. Dear Heavenly Father, we thank you for this day. I thank you again, Lord, for these students. Just pray you be with us today as we study your creation, and I just pray that we glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. Okay, so we have we're going to cover some introductory differential equations. And so, in the universe of all Calculus 2 classes taught in the United States, I mean, there's a variety of topics that are taught in this arc of the course, but we're going to focus here on just like first order problems. We're going to look at first order differential equations. So, but before I get into the specific material, I just want to talk about some terminology. It's a differential equation. So some terminology. First of all, what is a differential equation? Is blank. I'll throw in an and for you. Blank involving blank. Let's see here. What else do I want to tell you? An ordinary differential equation has blank independent variables. We'll fill in the blanks here in a second. A partial differential equation has blank independent variables. All right, so a differential equation this is really going to be shocking, all right? It is an equation involving derivatives. All right, very shocking, I know. I guess to be a little bit more specific, it's something of the form f of yn minus 1, dot, 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 y prime, y, possibly x equal to 0. So it's some kind of combination of some sort of function of independent variable x, the dependent variable y, and its derivatives out to some order. The highest order which non-trivially appears in the differential equation is called the order of the differential equation. So when I say a first order differential equation, I'm talking about an equation which just has the first derivative of the dependent variable appearing non-trivially. An ordinary differential equation has one independent variables. Questionable grammar, but the right idea. So sorry, I should have put a parentheses s here to hedge my bet. A partial differential equation has more than one. Sorry, I should have done like this. Poor planning on my part. Partial differential equations are really important. Ordinary differential equations are really important. Both of these, you can look at systems of differential equations, just like you can look at systems of equations, right? What's a system of equations? It's when you have more than one, right? So let's see here. For example, this is something maybe you've heard of. F equals to ma, right? So that is, if you expand it, really, fx is equal to m d squared x dt squared. Fy is equal to m d squared y dt squared. Fz is equal to m d squared z dt squared. All right, so this is a system. This is actually a system of 3 ordinary differential equations. Each of them has second order. And you might recognize this. This is Newton's second law. So solving physical problems in classical mechanics involves solving a system of second order ordinary differential equations. That's one example. Another example which is important in electrostatics. In electrostatics, there's something called the electric field. The electric field propagates the electric force, all right? And it turns out you can write that as minus the gradient of what's called the potential. That's the potential energy per unit charge, or the voltage function. Now, when you study electrostatics, you'll find out that the divergence of the electric field is equal to the charge density divided by the permittivity of free space. And when I plug the voltage thing into this, I get minus del dot del V equals to rho over epsilon naught, or just cleaning things up here a bit, so-called Laplacian, del squared V is minus rho over epsilon. There's a sub naught, permittivity of free space. Anyway, let me just show you what that is in detail. It's partial squared V, partial x squared plus partial squared V, partial y squared plus partial squared V, partial z squared is equal to minus rho over epsilon naught. So what we're looking at right here is a partial differential equation. All right. Finding the voltage function that stems from having a certain static distribution of charge involves solving a partial differential equation subject to certain so-called boundary conditions. We're not going to do these things in here. I just want to emphasize to you, of course, all I'm trying to get across to you is that differential equations are like fundamental to physics. They're at the heart of all of our modern descriptions of the world around us. But before you can solve these kinds of fancy schmancy things, you got to learn the basics, right? And that's where we are. What's that?
What is the little symbol?
Oh, these are partial derivatives.
We haven't memorized yet, right?
No, we won't do those.
L3. I'm wondering what the symbol is.
Oh, it's called partial x. It's really, really complicated. What it says is that you just treat y like it's a constant. So this is like 2xy. If you really understand what I just said, you can do any of them. What's that? What's that? Ohm's law. No, I mean no circuits here. No circuits. So I'll tell you what, I'll do a circuit in a little bit. Since you brought it up. All right. Yes, but anyway, I shouldn't get into partial derivatives. I personally think they can be taught to you guys in about a half hour, but whatever. All right. This is the charge per unit volume. It's the dq dV. So you can study that in our junior level course on electromagnetism here in the physics department. That's good. All right. So first order differential equations. Then, now that I've given you a little bit of the lay of the land, and this is just a pair of examples. I mean, there's these things called the Navier-Stokes equations. They describe like fluid flow. Quantum mechanics is based on Schrodinger's equation, at least semi-classically, and that's a partial differential equation in space and time. I mean, it's all differential equations. So when you study physics, it's all differential equations, at least for a while. So first order. But besides that, these first order differential equations, they also come up just in more like sort of mundane things, like if you want to study the temperature of a cup of coffee cooling or something like that. So I'll show you that. So first order, sorry, I have problems today. So basically here we're looking at something of the form dy dx equals to f of x comma y. Generically speaking, that's the kind of first order differential equation we'll look at in here. All right? And I tell you about 2/3 of the story here, Now maybe a half. The other half we leave for the differential equations course. All right? So to solve a first order differential equation, there are three main methods. Separation of variables, the integrating factor technique, and exact equations. All right, besides that, there's these things called substitutions, but we'll leave that for the DiffEq course. Now we can't talk about the exact equation method yet, because that involves these things, these partial derivatives. All right, so that has to be left for Calc 3 if your instructor is a glutton for punishment, or differential equations if your Calculus 3 instructor has more sense than I do. So that we'll focus here on the two methods we have to solve these sorts of things. Two methods. The one is separation of variables. The other is the so-called integrating factor technique. These are both limited in their scope, in the sense that they only apply to certain problems, but not all. All right? So let's get to it. It's really simple, this separation of variables one. So suppose you've got dy dx is equal to xy. All right? So what separation of variables says is separate the variables. Okay, sorry, I'm full of all sorts of profundities today. Let's see here, dy over y is equal to x dx, and then you know what you do? Yeah, we integrate both sides. So integrate. And of course, this gives us the log of the absolute value of y is equal to 1/2 x squared plus a constant. And there you go. Now that's, some people wouldn't accept that as a solution. I would tend to say that this is a kind of solution. This is what's known as an implicit solution. Sometimes that's all you can do. The reason it's implicit rather than explicit is because I haven't solved for y. Now the only thing that's keeping me from solving for y here is laziness. We can actually do it, right? We can do the algebra here. Solve for y, what do you do? E to the log of the absolute value of y is equal to e to the 1/2 x squared plus c, right? But that's e to the c times e to the 1/2 x squared by laws of exponents. This, on the other hand, is, if you allow me this short manga-style calculation, the absolute value of y. Also known, continuing my manga style, plus or minus y. I'm sorry, did I mispronounce that? Manga style. Is that better? You guys don't read the manga. Oh, sorry. So, it's never good when you have to explain the joke. All right, plus or minus e to the c, e to the 1/2 x squared. And so this e to the, plus or minus e to the c is just a constant, right? So we might as well just call it k and be done with it. Okay, so y equals k e to the 1/2 x squared, and there you go. That's an explicit solution. Now, it bothers me a little bit to say either of these are specific solutions. I mean, they are in the sense of differential equations, but in the sense of functions, these are not specific functions, right? As the c varies, what happens? You get different functions, right? But different solutions also. I mean, this is actually a solution set, right? I mean, the solution set, to be more specific, would be something like this. K e to the 1/2 x squared, such that, you know, k is a real number, something like that. In some sense. I mean, that doesn't quite do it justice either. I mean, it's a function. Well, anyway, for every different k, you get a different solution, technically, right? Let's see here. Don't ask me to graph that. I'd rather not. They're not related. But this is kind of familiar, right? What else did we do that had this sort of ambiguity in it? We've been doing it all along, right? So let me just take a break here from thinking. What if we want to integrate y dx equals to f? Let's equal to, say, g. I'm sorry, I'll get it eventually. I'm an idiot. F dx equals to y. What does that mean? What does it mean for the integral of f of x to be equal to y? What do we mean by that? Yeah?
I was saying it means that if you differentiate y.
Uh-huh. Right? What is that? That's a differential equation, right? So every time we integrate, we're solving a differential equation in this sense. So you've already been solving differential equations all along. So this is really just more of the same. There's another way to look at this, which is that differential equations is really just kind of a sort of indirect extension of integration theory, right? It's a way of undoing derivatives. But I mean, here it's really pretty much just integration. But as you go on, the ways we solve differential equations are a little bit sneakier. Anyway, but here, you know, what's the relation? If you have dy1 dx equals to f, and you have dy2 dx equals to x, how are y1 and y2 related? If two functions have the same derivative, what's their relation? Right, they're just related by a vertical shift, right? Supposing that the derivatives match on a connected subset of real numbers, right? If you had derivatives matching on like a disconnected subsets, you could have them differing by different constants on the different parts or something, but here you had just a constant, right? So the solution set to this, it's kind of boring, right? If you got one of the antiderivatives, then you just kind of repeat it, right? This was supposed to be exact vertical, and you know what I mean. I don't know why I did that. I should have gone something simpler like just lines but here, the way that these solutions are related for different k is more subtle, right? Here, let me do one that I can actually graph. All right, another separation of variable example. How about this one? dy dx equals to minus y over x. Oh, sorry, that's not what I want. I want minus x over y. That's more fun. Okay, so this gives me separating variables y dy equals to minus x dx. You integrate both sides, then what do we get? Uh-huh. All right. And then plus a constant, which I'm going to call r squared. Okay. And then, so that gives me, oh, I'm sorry, I meant r squared over 2. So that gives me x squared plus r squared, y squared rather, is equal to r squared. Why did I make the constant r squared over 2? So that this happens. I mean, you could call it a constant and then identify that fine, let me behave. Sorry, I was raised by physicists. They always do this sort of thing. They like integrate something and like, it's the square root of something divided by 73. And you're like, why did you write the constant that way? It's really weird. And then like 3 steps later, the square root and the 73 goes away and it's a pretty formula. And it's just like, that's just not cool. But it's how I was raised. Sorry. So, yeah. So I guess if I do the algebra, we should have 2c here, huh? No. Yeah?
C from the other side.
Oh, if we add it on one side, that's sufficiently general, right? I mean, if we add 2 arbitrary constants, one on each side, it's the same. Yeah. Now, if you think about this, what is the solution set? If c is negative, is there any solution to this equation? No, you can't have the sum of 2 positive. You can't have the sum of squares of real numbers equal to a negative number, right? So c has to be non-negative, which means that this is greater than or equal to 0. So that says that you can write 2c as equal to the square of some non-negative number, which we can call r. And of course that's worth doing because that's what it means geometrically, right? This is a circle of radius r. And so if I plot the solutions this time, the solutions look like this, right? Which is quite different than the solution set, the antiderivatives you get from your integration, right? Two solutions to two solutions to a first-order differential equations are not necessarily just related by a vertical shift. They can be related in much more complicated ways. There's much more interesting geometry here. Now, of course, this is a what? Again, this is an implicit solution, right? I guess technically this would be the general implicit solution. People say general solution, they mean it's not just one solution, it's a formula which has a constant in it, and as you adjust that constant, it allows you to cover all possible cases. All right, that's the idea of a general solution. If I wanted an explicit solution, then I have to focus my attention in different places, right? Like if I want the explicit solution to be for y greater than 0, the explicit solution is what? These sorts of things, right? But for y less than 0, the explicit solution is minus the square root of r squared minus x squared, right? What's the explicit solution when y is equal to 0? Can you find y as a function of x when y is equal to 0? So here it is, right? This is y equal to 0, right? Imagine that you could find an explicit solution, right? What makes it the connection between explicit and implicit solutions is they match up, all right? So like the explicit solution would also have to be like this, right? If you had an explicit solution around 0, y equals 0, it would be like this, right? But what does that fail? It's hard to see. My circle's not curvy enough. I have 2 red markers. What's the point of that? Yes, the vertical line test, right? It's necessarily double valued there, right? I mean, it's for a single x value, it's going to hit. Here, I'm going to make my vertical line not quite vertical to serve my purposes. Like that single x value would go to these 2 different. That's supposed to be a vertical line. Use your imagination. The point is, you can't solve for y as a function of x when y is equal to when you're at y equal to 0. Well, you can solve it to one side or to the other side, but you can't solve it centered around 0. All right. All right. Anyway, this is part of a much larger discussion that if you want to get into more deeply, you can come take advanced calculus with me when you're ready. We talk about it more in there. Okay, so let's see here if we can do another one. dy dx equals to e to the x plus y. Oh no. We can't separate it. Or can we? So what? You can't separate this, right, if you don't know algebra. But if you know algebra, this is an innocent looking, this is just a sweet little, honest, just harmless little separation of variables problem. See, you just do this is equal to that, and then you're good to go. But I've given this in differential equations tests before. It does seem to be harmful to about 35% of the population. You know, something like that. It's the warning label I put on it. Side effects include dropping the course, reduction of a letter grade. Not really, I mean, it's just a problem. Let's see here. Integrate both sides, we get minus e to the minus y equals to e to the x plus a constant. I really should do some I should really do like 2 to the x plus y sometimes, you guys. It's too late. So this is, all right, now here's where you guys get, this is fine. This would be the implicit solution, right? I'll talk more about how to find, we need to talk also about how to find tangent lines to these things. But I don't want to do that right this second. Now, can you find the explicit solution here? Right, so just take the natural log of this equation, right? It's negative. Oh man, we can't take the log. Whatever will we do? So what you want to do, multiply by minus 1, right? So this is e to the minus y, but that's exactly the problem. Minus e to the x minus c. You're like, oh, but now this is negative too. You know, see, that's just a matter of perspective. See, this you could rewrite as c bar minus e to the x, where you just let c bar equals to minus c. See, c is an arbitrary constant, so you can repackage that thing however you like, pretty much. In fact, for this to have a non-trivial solution, I mean an actual solution, you're going to need to have that the original constant was negative. All right. Anyway, now that we've got this and that, we can take the log of both sides. We get natural log of e to the minus y is equal to the natural log of c bar minus e to the x. One of the things I hope you're picking up on here is we have to add the constant when we integrate both sides. You can't integrate both sides, ignore the fact that you need to add a constant, and just da-da-da-da-da-da, and then at the end, oh, just add a constant. No! No can do'sville. Will not work. You will be wrong. Very, very wrong. It's one of the ways you can tell me, I don't care what you're doing right now. Please reduce my grade. Now, I don't think that's how you feel, so add the constant up here, and then you have to do algebra on it. Doing that algebra puts it in weird places in the formula, like right now. Okay, I'm just going to put a minus here. I know we could flip it, but I'm just going to leave it like this. And if it bothers you writing the answer with a bar, see, I could have, I don't know, I usually just, when I run into something like this, what I usually do is I put a bar up here and then I leave the one I work with as C. But it's too late, so there you go. Yeah. All right, so I'm going to show you guys all kinds of applications of this to, like I said, cooling coffee. And if I had done better today, I would have covered RL circuits and so forth. Well, maybe I'll still get to that. Yeah, let's just do RL circuits. So suppose you got a voltage source, and then a resistor, and an inductor, like so. All right, so this has resistance R, this has inductance L. Kirchhoff's voltage law says that the voltage is going to be equal to the voltage dropped, which in this case is by Ohm's law IR. Goodness gracious. Plus L di dt. That's the voltage across the inductor. In some sense, that's the definition of inductance. Well, not exactly. Anyway, so for different choices of E, you get different differential equations, right? So let's see here. Suppose all right, so let's see if I can rewrite this a little bit. I mean, I guess you could still do separation of variables here if you want, though. Fine. Let me see here. So I got di dt equals to what? E minus IR over L, right? And so if I separate variables, what does that get me? For reasons that are not entirely obvious yet, I'm going to pull a minus out here. So this is IR minus E divided by minus L. Now, with that in mind, that gives me DI over IR minus E. You're like, that's weird. Fine. But deal with it. dt over minus L. And I don't know, I still don't like this very much. I want to have I by its lonesome. So I'm going to multiply both sides of this equation by R, which gives me what? Yeah, di over I minus E over R equals to what? R dt over minus L. All right, I'm happy. I'm content. Now I'm going to integrate. I've done enough algebra so that my integration is easy, right? We're assuming that this is constant, by the way. You could, well, I'll explain more about what we could do when it's not a constant in a minute, but natural log the absolute value I minus E over R is equal to minus RT over L. You exponentiate both plus a constant, come on. All right. Fortunately, there's no capacitance in here, so there's no danger of confusion. You exponentiate both sides. You get I minus E over R, all right, is equal to plus or minus E to the C, E to the minus RT over L. And so there you go. I is equal to E over R plus some constant. Let's call it C. Again, I'll put a bar on this one there. Is it better? C E to the minus RT over L. And there you go. That's the current as a function of time in an RL circuit, where that constant depends on the initial conditions. Depends on how the circuit starts. All right. What happens as time goes to infinity? What do inductors do? They oppose a change in current, right? After the inductor's all charged up, it stops opposing a change in current, right? It's just all, its magnetic field's already established and current just flows through it. So after a few time constants, sorry, tau, it's a time constant, it's L over R, time constant. After a few time constants, the current has settled. This transient term goes to zero effectively after 5 time constants. It's like 1% of whatever it was to start with. And you're just left with E over R, which is just plain old Ohm's law, the voltage divided by the resistance. So. Now, if you don't know these things about circuits and stuff, that's fine. Most of you are going to take Physics 232 here, and you'll learn these things there or somewhere else. So, now, I don't always do this example this way. There's another way to do this example, because this actually is a place where worlds collide. We have an overlap of the separation of variables and the integrating factor technique. So let me show you the integrating factor technique. So a linear first order ODE has the form, in the standard form, is dy dx plus py is equal to q. So if you can write the differential equation and make it look like that, it's said to be a linear differential equation. All right? Now, I still have 12 minutes, right? Yeah, okay. Sorry, whenever, it's unnerving whenever somebody messes with their bag, it like makes me go, what? Oh no, what time is it? Okay, so separation of variables on this, little dicey, right? Because if you look at dy dx equals to q minus py, there's really no guarantee that you can make, I mean, think about that. Think about q minus py. Can you write q minus py as equal to like some first function of x times some second function of y for generic choices of p and q? I don't think so. All right. For example, dy dx, come on, dy dx plus, I don't know, 2 over x times y equals to I don't know, how about e to the x cubed? So, you know, if I subtract this to the other side, can you factor out a function of x times a function of y? No, you can't, right? The one's just a function of x, the other one's just a function of y. There's no common y to factor out. You're stuck. You can't do separation of variables on this thing, all right? So we need something else. And that's where the integrating factor technique comes in. So here's the thing you do. You let I, not this I, but I for integrating factor, be the exponential of the integral of p dx if we're working with x. If we were working with a dy dt equation, we put a t here, but it's the exponential of the integral of p dx. You say, well, that's great, but why are you doing that? Well, just stick with me for a second here. Then dy dx is what? What's the derivative of an exponential? It's the exponential, right? Times the derivative of the inside function by the chain rule, right? Don't forget the chain rule. It won't forget you. Let's see here. It will haunt your dreams. Let's see here. P. I mean, that's pi. Well, okay, fine. You got me. It's IP. Oh, man. Don't tell my kids. So this is I, right? And this is P. So if you go to the differential equation up here, star, multiply star by I, what do you get? You get I dy dx plus IP y equals to IQ. Right? Now, we haven't changed anything by doing that because the integrating factor is a exponential, right? Which is non-zero. So we're not going to gain or lose solutions in doing this. It's a harmless thing to multiply by, right? Okay, so before I go further, let's do that over here. So I'm going to work this example in parallel to the general derivation, if you don't mind. So let's see here. For this one, the I would be the exponential of the integral of 2 dx over x, also known as exponential of 2 times the natural log of the absolute value of x. That's exponential of the natural log of the absolute value of x squared, also known as absolute value of x squared, or as I prefer, x squared. So after a little bit of algebra and calculus, we find the integrating factor is just x squared. So I take my handy-dandy differential equation here, multiply star by x squared. What happens? I get x squared dy dx plus, well, let me just simplify if you don't mind. What's What's 2 over x times x squared is what? 2x y equals to x squared e to the x cubed. Something magical has happened, right? It happens over here too, though. Check it out. This is precisely the derivative with respect to x of the integrating factor times y. See, because IP is the derivative of I with respect to x. So by the chain rule, by the product rule in reverse, right? This product rule So, but we're going this way, so it's the product rule in reverse, right? But that happened. Did it happen over here? Is this d dx of x squared times y equals x squared times e to the x cubed? You differentiate x squared y, what do you get? You get x squared dy dx plus 2x times y, right? By the product rule and implicit differentiation. And what's the beautiful thing about this and that is you can integrate with respect to x, integrate with respect to x, and that gives me I times y is equal to the integral of iq dx. So therefore y is equal to 1 over the integrating factor times the integral of iq dx. There you go, that's kind of a general formula to solve any linear first order ordinary differential equation. And then here, of course, integrating both sides, what's the integral of a derivative? It's just the thing again, right, the function. So that just spits back out x squared y. And on the other side, well, I chose e to the x cubed because I knew the integrating factor was going to be x squared. And I knew then we could make a w equals x cubed substitution, which would make us happy. So x cubed equals w dw 3x squared dx. So this is really the integral of e to the w dw over 3. Ew. In other words, one third e to the x cubed plus a constant. Have to add the constant here, folks. Not later, whenever you feel like it. You got to deal with the algebra. And then y, solving for the explicit solution, is 1/3 e to the x cubed. Well, fine. So there's the solution. It's a linear. The what? Well, first order because it just has dy dx. So this, again, is the integrating factor. You're also not asking me about that, right? So I will tell you the more general story since you're asking. So a linear differential equation has the following property. You have L of y1 plus y2 is equal to like L of y1 plus L of y2. Maybe it's not the right way to say it for you guys in here. Yeah, it's probably not the right way to say it. It's not the right way to say it. How can I say this? That's not helpful. I mean, there's different ways of explaining it. Linear because it is just linear in the derivative and the dependent variable. There's no like dy dx squared or y squared or sine of y or e to the y or something like that. So the linearity here refers to the linearity of the dependent variable and its derivatives. Now what that means is that if you have solutions to a linear differential equation, there's an interesting structure, like the sum of solutions is again a solution, but not quite true here because of the Q. If you have 0 here, if you have a homogeneous linear equation, then the sum of two solutions is again a solution. And so it has a really nice structure, but this is the sort of thing we'll talk about in differential equations. I can talk to you more about it after class if you want, but
When you say the homogeneous, do you mean that like all its parts are on one side?
I mean, it's something like y prime prime plus 2y prime plus y equals to 0. Or it could be something like x squared y prime prime plus xy prime plus e to the x y. I mean, the y's have to appear linearly and the derivatives have to appear linearly, but the x's, in x you could have nonlinear functions, it's fine. But these are homogeneous because there's no, you can write a sum of the dependent variable, the terms involving the dependent variable and its derivatives equal to 0. There's no so-called forcing function. Like here, Q is a forcing function. If you rewrite this one, we have di dt, well, L di dt. Oh, it already is in the right form, I guess. I'm just rewrite it slightly. Plus IR is equal to E, right? So that's kind of the same if you want to compare. So the significance of Q is it's like the voltage applied. It's sort of the external thing happening to the circuit if you think about the R and the L as being sitting there on their lonesome and the voltage source just comes in and messes with them. In the context of Newton's equation that we talked about before, the forcing function literally is a force. But again, we're not going to talk about homogeneous and non-homogeneous equations. You guys keep asking, you keep tempting me to talk about differential equations, and there's another day for that, which is after Calculus 3 for you guys, so I'm going to stop. You won't get any more out of me. I refuse.
Do you teach differential?
I do. Sometimes. Right now. We got room if you want to add it. I got 6 students in there.
That's crazy. Don't you have to have calculators?
Technically, yeah, you have to have calculators.